Hello everyone, and welcome to today's webinar on Electrostatic Discharge, ESD. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Arm Sarkisian, General Manager of Engineering Sciences at EAG, will be answering some of the questions during the presentation, and we'll also collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Barry Fernelius, ESD and Latchup Manager at EAG Laboratories.
Well, thank you. I appreciate that. I'm Barry Fernelius, and as Rena said, I manage the ESD and Latchup Laboratories at Eurofins EAG. We have two locations in California, one in Irvine and one in Santa Clara. Here's an outline of today's presentation. It will appear again several times, and the bold text in red shows you where we are. So first, a little bit about the company. EAG was established in 1978, and our experience, combined with leading state-of-the-art technology and equipment, enables us to leverage the power of science and engineering to accelerate innovation through creative problem solving, objective analysis, and expert interpretation of data. That's quite a mouthful. We have several hundred highly educated and experienced employees working in laboratories around the world. We offer over 40 analytical techniques at our 22 locations. At Engineering Science Services, we provide an integrated model that supports semiconductor and microelectronics companies in the total product life cycle, from conception to volume production. Our services include ATE, reliability, ESD sensitivity testing, focused ion beam circuit edit, and failure analysis. We also have registered and accredited quality, military, and automotive systems. Well, before we talk about the details of the test specs, let's look at electrostatic discharge itself. No ESD presentation is complete without the obligatory lightning bolt picture, courtesy of NOAA. Electrostatic discharge occurs when differently charged objects are brought close together, or when the dielectric between them breaks down, sometimes creating a visible spark. So it's simple, right? If you don't see a visible spark, there's no ESD. Problem solved. Well, not exactly. The kind of electrostatic discharge that affects circuits doesn't require a visible spark to do damage to parts. And the main reason we do this kind of testing is simple. More than a third of field failures are caused by ESD and have been for decades. The types of failure mechanisms are listed on the slide, and you can read them for yourselves. But every time that we shrink circuit geometries, it makes the problem even worse. It makes the devices more fragile and susceptible to damage. Every time somebody tries to make devices faster, it also puts them at risk. Like most engineering problems, this is a design trade-off. In order to make a device faster, the ESD protection often ends up being compromised. As a result, ESD testing is and has been part of the JESD 47 integrated circuit qualification requirements for every IC we make. Now we're ready to talk about the scope of the ESD work that we do at EAG. There's an old adage that says an ounce of prevention is worth a pound of cure. Sometimes people ask me, are you in the business of doing auditing or setting up workspaces? Can you help me test our wrist straps or static dissipative bags? These are all things that are involved in the prevention of ESD events, and I've listed even more of them on the slide, and they're important. In fact, we use them when we're handling your parts, but we're just not in the business of selling these services. Instead of a focus on prevention, perhaps this slide should be called Services that EAG doesn't currently sell. Also, we aren't in the business of selling system-level ESD testing, charge board event testing, or cable discharge event testing. So what are we focusing on? Simple. We evaluate other companies' ESD protection circuits. And today we're going to talk about the human body model test and the charge device model test in a bit of detail. We're not going to talk about the machine model test because it's been discontinued. And if you want more information about why it's been discontinued, JEDEC JEP 172A has a comprehensive description. This document is available for free if you register on the JEDEC website. We're also not going to talk about the latch-up test, which could be a whole separate webinar topic. So first, let's take a look at the human body model. Here I've listed the standards for the human body model. Most often we're using the joint ESDA JEDEC standard, JS-001-2017, but I've also listed the mill standard method, the previous JEDEC, ESDA, and AEC specs. We can still do any of those, but we recommend that our customers use the most recent version of the joint ESDA JEDEC spec. The human body model originated as part of safety procedures in mining environments, where an ESD spark at the wrong time could cause an explosion. So this model has been around since long before we had ICs, and predictably it models a human touching an IC device. We're modeling stresses that happen to devices before they're mounted on PC boards, before they end up in systems. That's why for both the HBM and CDM tests, power is not applied to the device under test. At the bottom of the page, there is a simplified version of the circuit for the human body model. It's a 100 picofarad capacitor in series with a 1500 ohm resistor. Now the circuit diagram that I'm showing you is greatly simplified. Normally in the actual tester, in parallel with the 100 picofarad capacitor, there's a high voltage supply to charge the capacitor. So if you're going to do a 1500 volt ESD event, the high voltage supply would charge the capacitor to 1500 volts, and then it's disconnected from the circuit. When the relay closes, the ESD event is applied to terminal A, and terminal B is connected to ground. What the diagram also doesn't show is a charge removal circuit called the shunt resistor between terminal A and terminal B, so that after you've done a discharge, you don't leave any residual charges on the device. Here's what the resulting HBM waveform looks like when you zap the simplest device possible: a piece of wire, a dead short. I'm showing the current versus time waveform. The one on the left is from JS-001, and the one on the right is an actual waveform from one of our testers. They look remarkably the same. You measure the current versus time by using a current probe around the piece of wire and an oscilloscope. Remember, we had a 100 picofarad capacitor in series with a 1500 ohm resistor. The rise time for the waveform is allowed to be between 2 and 10 nanoseconds. Typically, it's around 8. Percent ringing has to be less than 15% of the peak, and on most testers being built today, that's not an issue. A perfect decay time would be 150 nanoseconds, but typically, again, it runs around 160 nanoseconds, which is well within the spec of 130 to 170 nanoseconds. And the peak is the HBM test voltage divided by 1500 ohms, plus or minus 10% in amps. So a 1500 volt HBM event has a nominal I peak of 1 amp because of that 1500 ohm resistor. If you looked at the waveform for a 500 volt HBM event, the peak would be about 0.33 amps, 1/3 of an amp. So some of the equipment that we have to do the test in our lab are Thermo Fisher Scientific MK2s. This tester has up to 768 channels, but really, we don't use it most of the time for devices that have more than 512 pins. There is a previous test board standard called a verifier board, which can handle up to 512 pins. Verifier boards are considerably less expensive than either MK2 boards or boards for the next tester, Thermo Fisher Scientific MK4. This tester has up to 2,304 channels. It's also backward compatible with the MK2 and verifier boards. We've tested devices with up to 5,000 pins, but to do so requires a custom MK4 board. Because the HBM test spec allows you to use representative pins for large power and ground planes, and I'll talk about that in a few minutes, we can design a custom board that can work for those higher pin count devices as well. So let's suppose that you want to do the HBM test. What do you need to provide besides the parts if you want to do HBM? First, we need a pin list, which identifies the supply pins, the non-supply pins, and the no-connect pins. I'll give definitions of those in a moment. If you're going to do curve trace, you're going to also provide curve trace parameters for each pin type. If you're going to do the table 2A test, again, which I'll be discussing in a few minutes, for each non-supply pin, we need to know its associated power group, associated ground group, and whether it's part of a differential pair. We also need a DUT board and socket to interface the part to the HBM tester and a test plan. We'll provide the tester and write the test program. Here are a few definitions that are important in HBM. Supply pins typically don't carry information. They just provide operating current. Both power and ground pins are considered to be supply pins for HBM. A no-connect pin is a package interconnect pin that is not electrically connected, just like its name suggests. It's not a test pin or some kind of diagnostic pin. That's not a true no-connect. A no-connect pin truly is an open. Doesn't have any connection to the die. Finally, all of the other pins that are not supply pins or no-connect pins are non-supply pins. These are the inputs, outputs, and IOs, the pins that carry all of the information when the device is operating. Now, the table on this page and the next shows the evolution of the HBM test. When I talk about the different ways that the HBM test has been done, I'll go through these changes, but in an abbreviated way. After the presentation is done, you'll have access to this video presentation. And you might want to go back to these two slides if you're interested in the details and the dates. As you might imagine, the HBM spec has changed a lot over the past 40 years. The first version of the HBM test, the mill standard, before there was a JEDEC spec, said you zap all possible pin pairs, 3 pulses per pin per polarity, 2 polarities, 1 second between zaps. The genius of this test is that it's both comprehensive and simple. And best of all, you don't need to actually know much about the part. This was fine for a while, but soon devices started to have higher numbers of pins. Back in 1979, there was a Motorola microprocessor called the 68000. It had 68 pins. You can do the math yourself. If you have 68 pins and you do all possible device pin pairs, that's 68 times 67 equals 4,556 pin pairs. 3 positive and 3 negative zaps 1 second apart, that takes 6 seconds. To test a single part then would take 27,336 seconds, or 455 minutes and 36 seconds, which is over 7.5 hours per part. This much tester time is very expensive, and a better way was needed. The mill standard was updated, and this resulted in a so-called legacy test called Table 2B in the current JEDEC spec. This introduced the idea of a supply group. Supply pins that are interconnected by metal on the chip or within the package, pins that are shorted together form a supply pin group. A supply pin that is not connected by metal to any other pins forms a single pin supply pin group. We discovered that what causes things to fail are when you zap a supply group to a different supply group, or you zap a non-supply pin with respect to one of the supply groups, or you zap a non-supply pin with respect to the other non-supply pins. And this allows us to simplify the test considerably. Let's suppose you had n supply groups. Remember, those are either powers or grounds. You ground the first supply group, and every supply group gets zapped, and every non-supply pin is zapped, except for the one that you're grounding, of course. You step through each of the supplies and do the same thing. Finally, there's the n+1 configuration. Here you ground all non-supply pins and float all the supply pins, and one at a time, you open up each non-supply pin and you zap it with respect to the other non-supply pins. Well, that saves a lot of time. And for a long time, that's what people did. Until that became too expensive when we started to have even larger devices. JEDEC companies worked together to do a study of HBM failures. They wanted to find out which of the 3 zaps of one polarity caused parts to fail. Some people had the opinion that the device is weakened by the first zap, weakened some more by the second zap, and the third one finally causes it to fail. When people went out and collected the data, however, they discovered it wasn't true. For a sensitive pin, it's the first zap that almost always causes a failure. So the spec was changed to 1 zap per pin per polarity. More data was collected, and they discovered that you could get the same results with a time between pulses of 0.3 seconds and later 0.1 second. They also discovered that when you were zapping supply groups, you could get the same result if you zap a representative pin for each supply group instead of all of the pins in the group. So now we're going to add another refinement. For every non-supply pin, remember the inputs, outputs, and IOs, designers know its associated supply and associated ground. So typically, each non-supply pin is associated with a supply group and a ground group. And zapping with respect to the other supply and ground groups that it's not associated with doesn't find anything new that the supply to supply test doesn't already find. In the n+1 configuration, where each non-supply pin individually is zapped with respect to all of the other non-supply pins grounded at the same time, failures were rare. For many circuit designs, the failures occurred when you ground one half of a coupled pair and zap the other half. These are also called, in most cases, differential pairs. So with these 2 considerations, and doing 1 zap per pin per polarity and using representative pins for power and ground groups, we end up with a new set of required pin combinations called Table 2A. The red sections show what changed from Table 2B. In this case, you still zap every supply with respect to every other supply, but when you're grounding supply group 1, you only zap the non-supply pins that are associated with supply group 1. And you do the same thing when you ground every other supply group, only zapping the non-supply pins that are associated with them. And when you've got 80 supplies, and maybe the non-supply pins are only associated with 4 to 6 of the supply groups, that greatly reduces the number of zaps that are required to do the test. Finally, the IO to IO test, the non-supply to non-supply test, has been replaced by one where you only zap the differential pairs with respect to each other. That is, the different halves of a same differential pair, because that's where failures are occurring. You also have the option of doing the non-supply to non-supply test from the legacy test, Table 2B. So this is Table 2A. For some extremely large parts, this is still too many zaps. So the final refinement in the latest version of the spec is doing a statistical sample of the non-supply pins in each of these cases. This only works if you have a large number of non-supply pins that have protection structures that are identical to each other. This option has other requirements that are fairly complicated. We're not going to go through the associated statistics in this presentation. Now, let's talk about what constitutes a failure when you're doing the HBM test. This is straight from the spec. Section 7, Failure Criteria. A part is defined as a failure if it fails the datasheet parameters using parametric and functional testing. If testing is required at multiple temperatures, testing shall be performed at the lowest temperature first. In other words, your ATE determines pass-fail for HBM, okay? Whoever manufactures the part has a test that they do that determines whether a part can be shipped to a customer. That's what determines pass-fail for HBM after the stress has been done. So we typically ask for parts that have been serialized, tested, and data logged before HBM test. We do the HBM stress and give them back to you, and your ATE results determine pass-fail. Here are the classification levels for HBM based on the highest voltage that the device can withstand. The most recent update to the spec added the 0Z classification, where devices that can't even withstand 50 volts are classified. Their withstand voltage is lower than 50 volts. There are also some updated procedures describing how to qualify the waveforms when they are low voltage. So here are all of the classifications. For a long time, Class 2 was the most common classification, which means the device can withstand 2000 volts, but it won't withstand 4000 volts. These days, I'm seeing more parts that are 1C and even 1B because of the constraints of the new processes and because of design constraints. There's an extensive discussion of these trends in the JEDEC document, JEP 155B. So at this point, stand up, stretch, take a deep breath, take a sip of your tea, deep breath in, deep breath out. Okay, now let's look at CDM. I'm going to focus on JS-002-2018. The other specifications that I listed are now considered to be obsolete. I'll talk about why in a minute. The CDM test is currently the most realistic ESD test. Just like HBM, it's an unbiased test. It models a device getting either a charge by friction, that is a triboelectric charge from rubbing against something like a part handler, or a part having a field-induced charge on it. Then some object that it's at a lower potential or ground touches it and discharges the part. The diagram shows the different parts of the CDM tester. There's a field charging electrode or field charging plate that has a layer of FR4, a dielectric, on top of it. The device is sitting on that, dead bug with the pins facing up. Above it, there's a ground plane. That's the blue crown plane that you see. And there's a pogo that has a 1 ohm radial resistor to ground. A voltage is applied to the field plate, which induces a charge on the device, and the robotics, the stepper motors, drive the pogo over to a pin, lowers the test head, and touches the device pin. Every pin, including no connects, is stressed the same way. In essence, that's it. The CDM test is not as old as the HBM test. It originated in the late 1990s, and at one time, there were 4 different CDM specs. ESDA had one, JEDEC had one, there was the AEC automotive spec, and the JEITA standard from Japan. Every one of them required a different test head, different procedures, different waveform specs, and different calibration requirements. With the exception of the JEITA standard, we still have the test heads for these old specs. And I have customers who still use them. Finally, after long hours of work done by a subcommittee of JEDEC and ESDA members working together, the two organizations released a joint standard in 2014 that was revised in 2018. And finally, in Rev D of the AEC Q100 011 spec, the AEC spec also references JS-002-2018. Because so many people have converged on this spec, that's the one I'm discussing today. So what was wrong with having 4 specs? First, there were 2 charging methods. You could do either a direct or a field-induced charge device model. Really, what happened in practice was almost everybody was doing the field-induced charge device model. There were a few companies who preferred to do a direct charge, but they were in the minority. The ESDA and AEC had the best waveform spec. JEDEC's waveform spec had a pulse width that couldn't be attained unless you added extra components to the test head, notably a ferrite bead. Each test head was made and tuned by hand, and as a result, each JEDEC test head was a unique object. There were no 2 that were quite the same, which is a real problem when you're trying to test at more than one lab or have more than one tester in the same lab. For calibration verification capacitors, the AEC and ESDA used an FR4 PC board with a simple pattern on it, a gold-plated round copper pad of a known size. This created the capacitor for the calibration/verification. It was inexpensive and easy to make. But because FR4 changes characteristics when it absorbs moisture and because it warps easily, this wasn't a good solution. JEDEC used more expensive disc capacitors with a ceramic dielectric, which are much flatter and much more stable. But the largest problem across all of the specs was metrology. So what's metrology? That's how you make a measurement. Consider this waveform from one of my old JEDEC JESD22-C101 test heads. On the left, that's what the waveform looks like on the screen when you're measuring it with a 1 gigahertz, 5 gigasample per second oscilloscope. On the face of it, it seems fine. Apparently, you can measure the rise time and see the peak. So what's the problem? The problem is it's an interpolated waveform. The scope is making up that waveform using the data points that you see on the right, those orange data points. That's not a lot of data points. And the bottom line is there weren't enough of them to accurately determine the peak, rise time, or pulse width. If you measure the waveform at 8 gigahertz, 40 gigasamples per second, suddenly everything becomes clearer. In fact, you can also see the high frequency noise that the ferrite bead adds to a C101 test head. And if you measure 3 or 4 C101 test heads, none of them look quite the same. You can't see it at 1 gigahertz, but you can easily see it at 8 gigahertz. Just to drive this point home, the diagram on the left shows 20 consecutive days of measuring eye peak on a C101 test head using a 1 gigahertz scope. When you compare it to the 20 measurements of a JS-002 head taken at 8 gigahertz, you can see that the new test head and the new test method, measurement method, is much more stable. All that was happening is that 1 gigahertz scope couldn't give you an accurate measurement of the peak. There was a lot of variation in the measurement. Once you increase the bandwidth, most of the variation goes away. So in summary, the committee used the best parts of the old specs and a few new ideas to create the new spec JS-002. First, everybody settled on field-induced charge device model, which was the common practice for most labs. The test head and waveform spec are similar to the ones described in the old ESDA spec, which means that it has a faster rise time and a narrower pulse, which is what happens in real life. The calibration/verification capacitors are the same ones used in the old JEDEC spec. They're much flatter and show less variation. Also, they updated the humidity spec. The old JEDEC spec was the only one of the CDM specs that had a humidity spec. It said that less than 60% relative humidity for the ambient in the room was acceptable. It turns out that the test has less variation at lower humidity. So in JS-002, they now specify less than 30% relative humidity at the test head. One of the new requirements, you have to use an oscilloscope with a bandwidth of at least 6 gigahertz when you're calibrating the tester. You're still allowed to use the 1 gigahertz scope when you're doing the daily checks, but we don't do that. EAG is standardized on 8 gigahertz oscilloscopes in all of our labs for doing both the calibration and for doing the daily checks. And finally, instead of emphasizing the plate voltage to define CDM, it's defined by the current versus time waveform that you see on the calibration/verification capacitors. So this is the JS-002 CDM waveform. The waveform on the left is the ideal one that's shown in the spec, and the one on the right is an actual waveform taken with an 8 gigahertz oscilloscope on one of our JS-002 test heads. The simplest CDM device is a capacitor. And for this waveform, we use the standard JEDEC disc capacitor, the small capacitor, 6.8 picofarads. The rise time is supposed to be less than 250 picoseconds. The real waveform shows 208 picoseconds, and it typically runs close to 200 picoseconds. The pulse width at 50% height is supposed to be 250 to 600 picoseconds. Typically, it's 400 picoseconds. For reference, remember the old JEDEC C101 waveform? Part of the reason the JEDEC spec had a problem was the pulse width at half height had to be 500 picoseconds to 1500 picoseconds wide. This simply isn't realistic. For the JS-002 test head, the peak is supposed to be 7.2 amps, plus or minus 15% for test condition 500, when measured with a 6 gigahertz or higher oscilloscope, which is what the 500 volt condition is now called, with an undershoot of less than 70% of iPeak. So here are a couple of pictures of our Orion 2 CDM tester. We also have an Orion 3 tester. Both of them use the same test heads. The bottom photo shows the plexiglass box that's around the robotics and test head. During tests, we run dry nitrogen to keep the humidity at the test head under control, and there's a sensor in the box that turns the nitrogen on and off as required. This tester can support all industry CDM standards, the old ones and the latest joint ESD JEDEC spec. You can do CDM testing with plate voltages up to 2000 volts, but the manufacturer only guarantees that it's in spec at up to 1000 volts. And this is acceptable because the new spec doesn't call for testing at 2000 volts anymore. Finally, we're using Agilent/Keysight 8 gigahertz oscilloscopes to check out the equipment and make sure that they're all in spec every day. So what do we need from you if we want to do CDM? Well, a pin list and curve trace parameters if you're going to be doing curve trace. And if you're going to be doing curve trace, it won't be done on the CDM tester. It's not capable of that. So we use the HBM tester to do the curve trace before and after. Of course, if you're doing a zap-only test, we don't need any of that. We also need a package outline drawing or a list of XY coordinates for each device pin. So we can tell the tester how to drive to the pins and lower the test head to touch each one. I also mentioned that you need a device whose geometry allows it to be tested on a CDM tester. Here I'm going to step back a little. See the flat plate in the upper picture? Devices that have no flat surfaces will rock. And sometimes we have to devise some clever ways of testing them. It's best if the device has a flat surface somewhere. Finally, you provide your test plan, and we provide the CDM tester and the test program. How are CDM parts classified, and how's failure defined? I could read the relevant portion of this spec to you, but the bottom line is that it's the same as HBM. Your ATE results determine pass-fail for CDM as well. Simple. And here are the classification levels. Most people used to attain classification C2A, but C1 is becoming more common. There's a good, but a bit outdated discussion of the CDM classification trends in JEDEC JEP 157. So now let's compare the two. Why do we have two ESD tests? The question that I get asked all the time is, if my device passes 1500 volts HBM, will that predict what it will do in CDM? And the answer is no, it won't. Here's why. I've plotted a CDM waveform and an HBM waveform on the same plot. The time scale is the same for both of them. It goes from 0 to 50 nanoseconds. And for the HBM waveform, you're not seeing the full exponential decay. This is just the first part of the HBM curve where you have the rise time, you reach the peak, and you're starting to decay. As I noted earlier, the rise time for the HBM waveform, the time to go from 10% to 90% of I peak, is 2 to 10 nanoseconds. The CDM event, in contrast, is all over in a couple of nanoseconds. Both of these waveforms show 500 volt events. The CDM peak current is over 7 amps for a 500 volt event, but the HBM, well, it isn't 3 amps as you'd suppose by looking at the scale on the left. In fact, it has to have its own separate scale. It's around 0.33 amps for the peak. I had to plot it on a scale that was 10x different so you could see it. So HBM damages with a waveform that lasts for a long time. It heats things up in your protection structures, and typically the failure mode is localized heating. CDM can do some localized heating as well, but its sharp, fast rise time punches through gate oxides, does other kinds of damage, sometimes in the core of the device. So you can think of one as a blunt object and the other as a sharp, pointy object, if you will, which is why they excite different failure modes and why you have to do both tests. Keep in mind in both cases, if you're going to do an electrical model for this, it's best to think of these as current versus time events. So I've already said CDM is faster and has higher peak currents, HBM is slower with lower peak currents, and as a result, they cause different types of failures. This might be the most important slide in the presentation. For the HBM test, the charge comes from an external capacitor. That is, the cost for the HBM event is external to the part. This lets you use protection circuitry from previous designs. You can leverage them. And if you change packages, the HBM performance of the circuit will only be affected in a minor way. It might not be affected at all. But in the case of CDM stress, the die package combination itself is what charges up. Back here, when we're looking at the peak current, that's for 6.8 picofarad capacitor. If your device has a lower capacitance than that, the peak will be lower. If it's larger and it has a higher capacitance, the peak will be higher. So consequently, if you change packages, you can dramatically alter the CDM performance. We had a customer who had a die in a fairly small package with about 0.35 millimeter pitch, and it passed test condition 500 with no difficulty. But then for another application, they took the same die and put it in a much larger package with 0.8 millimeter pitch. The larger package could carry much more charge. They were surprised when the device failed miserably at the same condition at which it had passed before TC500. So keep in mind that for CDM, the peak current depends on the die and package combination, and that's very important. I'm going to step through the job submission process. If you're going to submit a job, we'll send you all the proper materials. We'll probably end up having a telephone conference the first time to help guide you through it. First, we need to gather some information about the person submitting the job. I also need to know which tests you want to run and whether you want curve trace before and after stress. That's what the level 1, level 2, and level 3 is all about. I need an overview of the part. If you're submitting an HBM job or a CDM job with curve trace, I'll also need a pin list. For each pin, I need to know its type, power, ground, non-supply, or no connect. If you're going to curve trace, I also need current and voltage limits. If you're requesting table 2A, I need to know the associated supply and associated ground for each non-supply pin. Of course, if you're not doing table 2A, this doesn't apply and you can leave it off. The test plan shows the parts, their serial numbers, and the voltages at which they're supposed to be tested. Because of space constraints, I'm only showing the HBM plan, but in this particular example, I'd asked for a CDM test, so I'd need a CDM plan as well. Finally, the package outline drawing. This one is a generic PBGA with a 1 millimeter pitch. Package so old that we rarely see anything like this anymore. If you're going to do HBM and CDM testing, why should you come to EAG? First, we have 2 locations, Santa Clara and Irvine. So that means if one lab is out of commission, we have a backup. We have the same equipment set at both labs, the same procedures, and the same level of expertise. Also, if you have a package that we haven't tested before, you're going to need a custom circuit board design. We have an in-house PCB team that has designed hundreds of ESD boards. You can design it yourself if you want to, but if we design it, we'll guarantee that it's right the first time. We have other integrated services as well, including ATE. If we do the ATE, the part may never need to leave the building during the whole ESD testing process. Our other services include reliability testing, failure analysis, and focused ion beam capability. So if you fail in HBM or CDM and you want to know why, we have the tools to help you find that out. Finally, we also have ESD characterization tools. We have a low parasitic HBM tester, also known as an HBM 2-point tester from Grun Technical Solutions. And this could be the topic of a whole other webinar at some future date. We have transmission line pulse for characterizing HBM protection. And this year, we're adding very fast transmission line pulse to help characterize CDM protection. But most importantly, we have our highly experienced team that's been doing these tests for many years. We probably see more different ESD tests in 1 month than you'll see in a lifetime. Finally, why choose EAG in general? There are many good reasons, but I think it's important to state up front that client confidentiality is core to our business. And we're also a global leader for materials testing services, with a broad range of instruments and expertise that leave us poised to take on even the most challenging materials and engineering related issues. Finally, in light of the pandemic, we're committed to the safety of our staff and clients. We're open, but we may have limitations in how you can visit. Of course, this is going to change as people become vaccinated. Please contact us and we'll work with you. When people haven't been able to visit, we've been able to do video conferences on the test floor to make sure that you can stay connected with our team while we help you to solve your problems.